Let's talk now about the global pattern of volcanism and connect the global pattern of volcanism to plate tectonics. So looking at this, we have both the plate tectonic boundaries on Earth laid out in black, and also individual spots where volcanic eruptions are known to have occurred, noted in red. So the red dots are volcanoes. The black lines are plate tectonic boundaries. And what do we see? We see that mostly the volcanoes are isolated at tectonic plate boundaries, with just a couple of exceptions at places that we've talked about. This is Hawaii here, and that represents a hotspot volcano that's erupting there, but that's not occurring at a plate boundary. Whereas for the most part, volcanoes line these plate boundaries in certain spots. What types of boundaries do they line? Certainly they line a lot around what we call the Ring of Fire, which is basically this whole area here, ringing the Pacific. They also appear at some other spots, right? Like Iceland and in the mid-Atlantic. And also this East African Rift Valley. And then other places too, like there are some along the southern coast of Europe. For the most part, that's most of where the volcanoes are on Earth's surface. And those are all at plate tectonic boundaries, mostly either divergent plate boundaries, like in Iceland, like the center of the Atlantic, like the East African Rift Zone. Either continental or oceanic divergent boundaries can have volcanoes. Or they are at spots that are convergent boundaries that involve at least one plate being oceanic. So somewhere like Japan or the Philippines, these are ocean-ocean convergent boundaries that are generating chains of volcanic islands. Somewhere like the west coast of South America, that's an ocean-continent convergent boundary. The west coast of North America as well, up in the Pacific Northwest, an ocean-continent convergent boundary. But if the convergent boundary has two sets of continental plates, like the convergent boundary that's between the Indian microplate and the Eurasian plate that generates the Himalaya, there's really no volcanoes there. Why is that? Because there's no subduction there. So most of these eruptions are either associated with subduction in the case of convergent plates, or they are caused by divergent motion. And remember that the eruptions that happen at those divergent plates are caused by partial melting of the mantle due to decompression. You're taking the pressure off, and that allows some of the solid there to turn to liquid. You might want to look at this diagram and just come up with some example places that would have, say, an ocean continent or an ocean-ocean convergent boundary that could produce some of these volcanoes. For the most part, if a convergent plate boundary is involved, a lot of these, I'll note now, tend to be stratovolcanoes. Because there's some mixing of magma types that go on there. So here's a good summary of all that. So we have basalt producing spreading centers coming from partial decompression melting of the mantle. Volcanoes form along the axis of that mid-ocean ridge at those oceanic divergent plate boundaries. They also form at continental divergent plate boundaries too. At convergent boundaries, places that plates are coming together, you can form volcanic island arcs like Japan, like the Philippines, that represent ocean-ocean convergent plate boundaries, or they can form in continental volcanic belts, like off the west coast, like on the west coast of South America, continent-ocean convergent plates. Volcanoes also happen at hotspots, which aren't at plate boundaries, but they're more isolated. Here's a diagram where you can see some of these happening, an example of a continental volcanic belt at the subduction zone, the mid-ocean ridge that forms at a divergent zone, and the either isolated volcanoes or sort of linear volcanic features that form it there. You have active volcanoes over hotspots, like here, like here. You also have island arcs that form where oceanic plates are converging. One of them subducts and generates a line of volcanic islands, all of roughly the same age. Here's a nice summary slide if you want to just read what I was talking about. I want to note something about understanding hotspots and thinking about how the plates have moved over time. Hawaii is a good example. If you follow the line of Hawaiian volcanoes, they dive under the surface eventually, but then they continue out to the northwest in the Pacific, and then they actually take this sharp turn. And that's around 42 million years ago, 43 million years ago. These have been generated because the Pacific plate itself, the whole plate moves relative to the hotspot, and it's been moving to the northwest. So that something, right, 5.5 million years ago used to be there, and then something 42 million years ago used to be over the hotspot, meaning that in order to move to restore the way that we see things today, the Pacific plate must have been moving to the northwest. Take some time to wrap your head around how we can determine the motion from the age of the plates. You want to look in the direction that the volcanoes are getting older to know the direction in which the plate is moving today. It's a little counterintuitive. Here's a zoom in on that diagram. So if you have a hotspot and your plate is moving in this direction, it's going to build a volcano, and then your plate is going to shift. The whole plate is going to shift, and then you would build another volcano on that section of plate. And your plate is going to shift, and you build a new volcano on that section of plate. What that means is that you have older volcanoes over here, younger volcanoes here. And if you want to know the direction in which the plate is moving, you actually want to go from younger to older. That's the direction the plate is moving. We can get that same idea if we look at the Yellowstone hotspot, and we can look at the Snake River Plain over here and all the chain of volcanic deposits that we see there. We can actually tell the North American plate is moving southwest over the Yellowstone hotspot because of the ages of these, right? So these are 15 million years ago up to the Yellowstone hotspot today, which has erupted 3 times in the past 2 million years. It seems to erupt every 600 to 700,000 years. And the last time it erupted was about 600,000 years ago. We also have these large igneous provinces that are left behind. They're covered in flood basalts. We can see several spots on Earth's surface that are associated with those. The Columbia River flood basalts are a relatively small one, but there's also large ones that often get talked about in India. The Deccan Traps and the Siberian Traps in northern Russia are very large areas that are covered, at least at a particular point in time, by these big flood basalts. How do these flood basalts form? Here's our current hypothesis explaining it. They result, we think, from mantle plumes. And so these mantle plumes are going to start rising from the core mantle boundary, we think. And then this plume is a very large area that it's covering. Once it hits the surface, it's going to erupt in many different spots. It impacts on that lithosphere, and then it starts to come up through all these different fissures, generate large flood basalt deposits as the first thing that's coming out from one of these plumes. And then as the plate moves over the rest of the plume, now we've just got a small hotspot forming, and you will start to form a chain of hotspot volcanoes away from that. So much like lines of hotspot volcanoes, we think that mantle plumes are also associated with these large flood basalt that get left behind in these big igneous provinces.